Okay, I want to do one more Gauss's law problem. Probably the most important one because this is the one you're going to be writing up for me in a group assignment. So we have a cylinder of radius r, infinite cylinder. Radius capital R with charge density. Because it's infinite, we have an infinite amount of charge total. Charge density rho, and that's going to be measured in coulombs per cubic meter. So we've got, here's capital R, and this thing goes on forever, up and down. Okay, and we're going to find E at a distance R from the line of symmetry. Which is obviously right through here. Okay, now we got to do this in two parts. We have to do part one inside. R is less than capital R. So we have to draw a Gaussian surface that's going to exploit the symmetry of our physical situation. It needs to have the same kind of symmetry. If it doesn't, Gauss's law wasn't going to do us any good. So the symmetry we have is a cylinder. Let's use a cylinder. Let's use a cylinder. Radius little r and length L. So let's draw that in here, and that's going to be smaller. So that's L, that's the length, and little r here is smaller than big R. The cylinder does not go all the way out to the edge. Okay, so there's my Gaussian surface. I've drawn a picture and I've labeled that picture. That is a required step for a complete write-up. Okay, now we're going to make the same arguments we were making before. We'll use purple. So first off, a note. E, the vector, must point radially out. We know what the electric field from a line of charge looks like. We did that one last time. It was this one. For the exact same reason, the electric field had to point away from the line. This thick cable we got here, the cylinder of charge, is just a thick line. That's all it is. So E has to point radially out. So these are E vectors, all these purple ones. It wouldn't make any physical sense in the universe for E to point in any other direction. Like if it pointed up at some angle here, everything is symmetric here. There's no special relationship between up and down. I could rotate this whole thing around and nothing should change. And I could also rotate it around like this and nothing should change. It wouldn't make any sense for E to be bigger over here than back here. Everything should be radially, cylindrically symmetrical. So that means here on the surface of my cylinder here, I'm going to have all these vectors. All the purple ones are E's. So I've got three different surfaces here, and I need to think of them separately. So I don't know, maybe green. This will be surface number 1 up here on the top. Surface 2 will be the bottom, and then surface 3 will be the label of the soup can. Okay, let's draw in some normal vectors. I'll do red for these. Normal vectors are perpendicular to the surface. That's what normal means. So that's supposed to be a little right angle there. I'm drawing in little vectors and showing that they're perpendicular. Up here, here's a little normal vector. So the normal vectors n hat, this is what I'm trying to draw up there, n hat. Okay. So let's look at each one of these spots. On surface number 1, the normal vector points up, E runs along the surface. E is not passing through that surface. So the normal vector will be perpendicular to E. So when we do double integral of E dot ds, dot product of perpendicular vectors is 0. So flux number 1 is 0. No flux flows through the top of the cylinder. Same on 2. I'm just going to say that here. That's down here. It's the exact same scenario. The normal vector points down, E points right along the surface. It's a right angle. Okay, what about on 3? E's pointing out, radially out, so is the normal vector. E is parallel with the normal vector. So the double integral of E dot ds will just be double integral of magnitude of E ds. The dot product of parallel vectors is the product of the magnitudes. Okay, now we'd like to pull that E out. That only works if E is a constant on that surface. E is not a constant everywhere. It's not a constant up here on the top of this thing. Up on the top of the soup can, E's not constant. Doesn't matter. The flux was 0 there. On this surface, though, on surface 3, E must be constant in magnitude. Must be constant. All the points on this surface are the same distance away from the center. The universe literally can't tell the difference between this spot right here on the label and this spot on the label. I could rotate my coordinate system around and turn one of those into the other. E has to be the same because they're all the same distance away from the axis of symmetry. Okay, so because of these two statements, I can say flux number 3, which by definition is the integral E dot ds, must be double integral magnitude of E ds, which will be, pull that out because it's a constant, integral ds. This, by definition, the double integral ds, is just surface area. So that's the surface area of the label, not the whole cylinder. So this had length L, had radius R, and we're only talking about here, not the top, not there, not there. I'm crossing those out, meaning not there. If you were to unwrap that, if you were to get a Campbell's soup and take the label off, it would be a rectangle that's L high and this long. That's the circumference, 2 pi r. So then flux 3 is that magnitude of E times surface area, 2 pi r L. Let me make that pi a little better. Okay, now that's supposed to equal Q enclosed over epsilon naught. So let's deal with this guy. So put a little star there, star. Q enclosed is always going to be some version of volume enclosed times some density. My density here was coulombs per cubic meter, so volume enclosed is literally volume here. It's going to be cubic meters. So what's my enclosed volume? Where does my charge live? It lives here in this cylinder. So that's the volume of the little cylinder. The big cylinder goes on forever. It has infinite volume. Volume enclosed. So here, maybe I'll draw, like, here's big R. This was little r. That's an R. And this was L. Volume enclosed is just area of or volume of a cylinder. Pi little r squared L. Okay, so we can put those together then. E 2 pi r L, that's right here. Supposed to be Q enclosed. So here, let's write this out here. Q enclosed is volume enclosed over epsilon naught. So this is supposed to equal pi r squared L over epsilon naught. Now, the electric field might depend on R, little r. It absolutely cannot depend on L. It can't depend on the length of the cylinder because I made that up. Like the directions even say here, find E as a function of little r. That'll be my only variable that I'm introducing in the final answer. So look, the L's cancel out. They better. Pi cancels. That's just a coincidence. One of the R's cancel. I get E equals, I got an R left over and a 2 epsilon naught. Oh, I do this all the time. I left my row off there. And I did the same thing here. Oh, okay. Wait a minute. Hold on. I put in the epsilon naught in Q enclosed. That's not where it goes. It goes here. This was Q enclosed. Volume enclosed times rho. There's Q enclosed over epsilon naught. So I should have a rho here. Oh, I'm still on erase. Okay, so this is inside again. I'm only halfway done. This is inside the cylinder. That's for R less than capital R. Now let's do outside. R bigger than capital R. So I got to draw a brand new picture here. That old picture isn't going to work. And this is where people get this one wrong. I guess we'll use blue here. So I'm going to have some cylinder that looks like this. Again, I have to label my picture. You should never, ever draw pictures that you don't label the dimensions of. And here's little r. Okay, pretty much everything is the same. So I don't have to reinvent the wheel here. Here's surface number 1, surface number 2, surface 3. Like, I can say same arguments as above. Or with all the E dot in and all that stuff. I can say flux number 1 is 0, and so is flux number 2. There's no flux flowing through the bottom or the top. For number 3, that green is kind of out there. It's burning holes in my brain. So I'm going to switch to a different color here. Flux 3, same as before. E dot ds. Nothing's going to change here. That's magnitude of E. ds. That's going to be 2 pi r L magnitude of E. That's all still the same. Here's where things get interesting. Q enclosed is now different. So here's my cylinder of actual charge. My Gaussian surface went outside there. The charge only lives right here. All the charge lives inside this region. The charge doesn't come all the way out here. So the charged enclosed is only this cylinder that I've blacked in here. This is the charge. So the volume enclosed will be pi capital R squared L. That's the volume of this darkened in cylinder times rho. So now putting all this together, 2 pi R L magnitude of E equals pi R squared L, or capital R squared L, rho over epsilon naught. You got to keep your little r and your big R separate. They mean different things. The L's cancel. The pi cancels again. And we get magnitude of E is capital R squared rho over 2 little r epsilon naught. I'm just staring at that, making sure that's correct. Make sure I didn't miss anything. What did we get up here? So notice inside the cylinder, the electric field is going up. It's increasing because as you go out, you've got more and more charge inside your Gaussian surface until you reach the edge, and now you're not getting any more charge. You're just getting further away from your charge. So if we were to graph this out, here is our distance from the axis of symmetry. Here is the magnitude of E. At first, it goes up linearly. It goes like R. And then once we reach the edge of the cylinder, we drop off. This goes like 1 over R. Something similar happened with a sphere of charge. Only there, outside of a sphere, it drops off like 1 over R squared. Okay. Really, that's the only problem I wanted to do today. I'm going to upload this document. I'll give it a name. I'm going to upload this in the announcement that I'll make once I post this video. So there's one more Gauss's law problem we could do, the slab of charge. Maybe we'll do that later because it's a fun one. But that's a good place to stop here.